Assalamualaikum everyone, welcome to the course of real-time embedded system. So we will continue our chapter number 5, program design and analysis, lecture number 28, and today we will talk about optimization for energy, power, along with the program size, and finally we will talk about the validation and testing of programs. So let's get started. So in previous lecture we have covered program level performance analysis. We also covered optimization for execution time. Today we will cover energy, power, and program size reduction, and finally we will look into the program validation and testing. So as you know that energy is the ability to work, whereas power is energy per unit time, and both are very important in battery powered system. However, it is also important for wall plug-in system because more power means more heat dissipation. So we want to keep the power down as much as possible in order to overcome the heat. So this slide shows basically the depiction of how we can measure the energy consumption. So let's execute a loop. So here we have a loop, and what we are doing, we have a while true, it means the condition is true, and then we have some body of the loop. So what we are doing, we are just measuring the current. So by doing so we can measure the energy consumption of this loop. So let's say we have input that is volts and then the current flowing is I, so we can ultimately measure the power, and from there we can also measure the energy. So as in our previous slide we discussed that we can have some loop running on the CPU, then we have ampere meter that is measuring the current, and then we have a power supply. So measuring the current we can know the energy consumption of the program. So what are the factors in energy consumption? So these are the three factors that will affect the energy consumption of a program greatly. So number one is energy consumption varies somewhat from instruction to instruction. So it depends upon your instruction. Energy consumption varies from instruction to instruction, and also it varies with the sequence of instructions. So if we have some instruction earlier and then we have some instruction afterwards, if we swap those instructions we will have definitely change of energy consumption. So we need to arrange the instruction in a sequence that it has minimized the energy consumption factor. Finally, the opcode and the location of operands does matter as well. So opcode basically tends to tell us what is the addressing modes, like is it memory to memory, memory to register indirect, and then the location of the operands, where does they reside, like are they in the register or are they in the memory. So and what kind of operation basically we are performing, so that opcode tells us. If we are doing move, okay, that's going to take less time, but what if we are doing multiplication and we are doing floating point multiplication? So obviously the opcode that tells us the kind of operation that we are doing on these operands. So all these factors contribute to the energy consumption. So we can select those instructions which are energy efficient. So energy consumption varies from instruction to instruction. Sequence of instruction does influence the energy consumption, and finally then opcode and the operands. So in this slide we are going to talk about the sources of energy consumption. So according to Cathor and et al., relative energy per operation. So relative energy per operation, for example, memory transfer will take 33%, external input output will take 10%, SDRAM write will take 9%, SDRAM SRAM read will take 4.4, multiply will take 3.6, and add will take 1. So this is the energy, relative energy per operation. So this is kind of energy, so we can just say like out of 100% it's taking like 33 external input output, taking 10%, SRAM write taking 9, read taking 4.4, multiply taking 3.6, and add finally taking 1. So these are the sources of energy consumption according to this paper. So the behavior of the cache greatly influences the energy consumption of a program. So energy consumption has a sweet spot as cache size changes. So we need to take care of the cache size. We cannot go for a very long cache, neither we can go for a very small cache. So it's a trade-off. So we need to maintain a size that our cache will perform best. So for example, cache too small will result in program thrashes, burning energy on external memory access. Because the cache memory is too small, we cannot put all the program. So program thrashes, burning energy, so it will waste energy on external memory access. Whereas if cache is too large, cache itself burn too much power, because the program, we have to search for all the memory location in the cache, so program burns itself. Means that we have to do too much work in the cache. Okay, so neither we can go for very large, neither we can go for too small, but we need to have a compromise between these two. So cache does play an important behavior in energy consumption, and as the way cache size changes, our energy consumption changes. So optimization for energy, like we want to optimize our energy for a program. So first order optimization means that low energy means high performance. Okay, so what we are going to do, we are going to use memory in a page mode. Page mode means that we are just going to give the address of the row, and the column addresses will be automatically calculated from the first column address. So initially we will provide the address of the row and column, and the next column addresses will be automatically calculated, so that we can access the whole block in a cache. Now second is we can analyze cache behavior. If there are instruction conflicts, we can rewrite code or we can do rescheduling. If there are conflict in scalar data, we can move that scalar data anywhere else in the program. And if we have array conflicting data, as we have discussed in our previous slide, if two arrays are trying to access the same cache block, even though the location of two arrays are different, the conflict can occur. So what we can do, we can move that array, one of the array, or either we can do array pairing, and we can use register efficiently. So if we have limited amount of registers, so once the register is released by some operation, we can again use it. So reusing of the registers. And in addition to these points, we can do moderate loop unrolling. I have told you what is loop unrolling. So moderate loop unrolling eliminates some loop overhead instructions. We can eliminate pipeline stalls. We can look for the instruction that create pipeline stalls, and we can eliminate those pipelines. Inlining procedure may help. So if we are using the function, the procedure, and the procedure body is in the same code, so it will help us reduce the linkage, because we are not transferring the control from one file to another file. So as I've told you about loop unrolling, so we can loop unroll. It means that rather than having one tile, we can have two tiles. So just go back and check it out, like what was loop unrolling. So it means in loop unrolling, basically we create nested loops. So initially if we have like two loops, we will create four loops. So that was about the energy and power consumption. So we discussed that how we can optimize the energy and power of the program. Now we'll discuss about optimizing program for size. So the goal is to reduce hardware cost of memory. So if your code is small size, it will reduce hardware cost of memory, because obviously it will require less memory, and less memory requirement means reduced power consumption of memory units, because you're going to use less memory units, so power consumption will be reduced. Now there are two opportunities by which we can do that. Either we can work with the data or we can work with the instructions. So either we can optimize the data or we can optimize the instructions. So let's check it out how it works. So as discussed in previous slide, that we can minimize our program size and optimize it. So number one way of doing is data size minimization. We can reuse constant variables, data buffer, in different parts of code. Rather than using them at once, we can take advantage of reusability. So we can reuse constant variables, data buffers in different parts of code. Now, doing so requires careful verification of correctness, so we are not like updating something which is required later. So this obviously requires careful verification of correctness. Now, generate data using instruction, or we can generate data using instruction rather than generating data manually. So this will minimize the data size. So let's move on to next slide. So the second part is of program size minimization is reducing code size or instruction size. Both are same. So how we can reduce code size? We can reduce code size by using functions. We can avoid inlining function, because in inlining function, if we have to call a function 5 times, we're going to write the body of the function 5 times. And we can avoid loop unrolling, as I've told you in previous slide, that loop unrolling means that if we have like 2 loops, we are going to convert it into 4 loops. So there will be like, we create a set of nested loops for each loop. So if we do so, obviously our energy consumption will be reduced, but our code size will be increased. Use specialized instruction where possible. So rather than using general instruction, we can use specified instruction where possible. Choose CPU with compact dense instruction. So we are going to choose compact and dense instruction. Rather than having a big instruction, we need to choose compact and dense instruction. So obviously if you follow all these steps, our code size will be reduced and our program size will be optimized. Now coming to the final topic is of program validation and testing. So we need to know how much testing is enough to make sure our code is or program is working fine. Software standards of thoroughness. So we'll talk about software standard of thoroughness. Major testing strategies are clear box and black box. Clear box also means white box does look at the source code. So in clear box we do look at the source code. In black box we do not look at the source code. So let's get started and see how we can test a program and validate it. So as I've told you in previous slide, clear box or white box testing means that we will examine the source code to determine whether it works. Can you actually exercise a path? Do you get the value you expect along a path? So we are going to see that if we know that if we follow certain path, we will get this value. So we need to verify that if we follow a certain path, are we getting our desired value? Can we actually follow a path? Now, testing procedure. How we can test this, that we are exercising a path and we get an expected value along a path. So testing procedure include controllability and observability, and in between them is execute. So obviously once we execute our program, we can examine the output. So in controllability, we provide program with inputs, then execute it, and then observe the output. So it means that we are examining the source code. So once we have the source code, we can know how our control is transferring from one instruction to another instruction. So that is actually talking about path. And along that path, what values we are getting, it depends upon the controllability, because from controllability we are going to provide the inputs, then we are going to execute it, and then we are going to check it through observability. So let's move on to the next slide. So let us consider controllability by examining the following FIR filter with limiter. So this end one is limiter. As you can see here, this is our limiter, and then we have FIR code. So initially FIR1 has 0 value, and in controllability what we do, we provide with input values. So must fill circular buffer. So this is circular buffer here and here. So we must need to fill circular buffer with desired n values. Other code governs how we access the buffer. So now if you see at this statement, this top for loop, this compute buffer multiplied by c in bottom part of the circular buffer, because j start from current and k start from 0. So what we are doing, we are computing this do multiplication in bottom part of the circular buffer. However here j start from 0, so we are computing c into buffer in upper part of the circular buffer. So this is for lower part and this is for upper part. Okay. The above code computes the output of FIR filter from circular buffer of values and then limits the maximum filter output. If we want to test whether the limiting code works, we must be able to generate two out of ranges values. So these are two out of ranges values, greater than 100 or less than minus 100, positive and negative. To do that, we must fill the FIR filter circular buffer with n values. Obviously, if we want to check this, that whether it is out of range or not, we must need to fill the circular buffer with n values. Although there are many set of values that will work, it will still take time for us to properly set up this filter output for each test. Now this code also illustrates observability. As we told you, observability, we want to examine the FIR out before limiting tests. So we want to examine this FIR out and this FIR out. And this FIR out is basically, these are limiting. So the code also illustrates an observability problem. If we want to test the FIR filter itself, we look at the value of FIR before the limiting code. Okay, execute. We could use a debugger such as some breakpoints, and we break our code here at this point, so we can check FIR out before limiting it. So if we want to test the FIR code independent of the limited code, we would have to add mechanism for observing FIR out independently. So we are observing the code before the limiting, and then we are filling the circular buffer with n values. So these are the two things that we are doing in controllability. We are filling the circular buffer, and then other code governs how we access the buffer. So this is how we access the buffer here for lower part of the buffer, here for the upper part of the buffer, and these two lines are the limiting before the limiting test. So if FIR out goes out of range, for positive value we will set FIR out to be 100. If it goes less than minus 100, negative, we will set minus. So this is limiting code. Execution path and testing. As we have discussed in clear box testing, we need to know what path we are taking and what data we are getting along the paths. So paths are important in functional testing as well as in performance analysis. So most of the time for path analysis we make a CDFG, control data flow graph, to see what paths we are following and on how many operations we are following during that path and what are the values. So in general, an exponential number of paths through the program. So usually we have an exponential number of paths through the program. Show that some paths dominate other. Obviously some paths will be followed more rapidly, more in time, and other will be followed less depending upon the condition. So heuristically limits paths. So on the basis of conditions, on the basis of our history, we limit paths. So let's see an example of this execution paths and testing. So in this slide we will talk about two possible choices for a set of paths to test. So number one is execute every statement at least once. So these are statements that are in rectangular boxes, and these are directions in branches. So we are going to test each branch direction at least once, and we are going to check each statement at least once. So we'll get to know the possible sets of paths. So if we start, this is one direction. So this is one set of path. The other is this one. And if you see that there is one other path, this one, the last one, which is not defined, although there are no statement involved in this path. The branch, if we say this is like A, if this is A, so this leaves branch A out of the lower condition. So this lower condition uncovered, so we are not covering this condition. To ensure that we have executed along every edge in CDFT, we must execute third. So we have executed this, we have executed this, however we haven't executed this. So we must need to execute this to make sure that we have executed on every edge of the CDFG. This part does not test any new statements. As you can see here, we go from here to here, so no new statement. But it does cause A to be exercised. However, we need to test A. So we need to test every path in the program. Okay, so let's move on to next slide. So in this slide we are going to talk about branch testing. Heuristic for branch testing involve, like the method for testing branches involve, exercise true and false branches of conditional. Exercise every simple condition in the conditional expression at least once. So we need to exercise each condition, and we need to exercise true and false of branches. So let's have an example of this. So in this slide what we are going to do, we are going to branch testing example. As we have told you in previous slide that we are going to exercise true and false for each branch condition, and we are going to execute each statement. So if we consider test that A is false and this B greater than or equal to C is true, then this condition will execute because A or B greater than C. So if any of the one is true, we're going to print OK. But for this particular condition, which is incorrect because we are using AND here, so if either of them is true but both of them are not true, we are going to get false. So this is the example. If for example A is 0 and 3 greater than or equal to 2, then we'll get to going, this statement will be true. Whereas if 0 and 3 is greater than or equal to 2, because both are not true, only the later one, 3 is greater than or equal to 2, is correct, so we're going to get false. So we're going to check each conditional for true and false. So here we have another example of branch testing with the correct code and with the incorrect code. In correct code we are doing the comparison or the testing, whereas in the incorrect code we have done assignment. So in C, this statement will execute and good pointer value will be stored in X. However, this is incorrect. Incorrect code changes pointer. Assignment return new left hand side in C. So this side will be new. So how we can test this out? We can test this out using our previous false and true test. So if we say that this is false, X is not equal to good pointer, X is not equal to good pointer, and X pointer field equal to 3. So this is obviously going to be false. We are going to get error because previously we have put the value of good pointer in x. So obviously this is going to be equal, so we are making it not equal, so this is going to be wrong. So if we apply the principle of branch testing, one of the tests we want to use is this, x not equal to good pointer. Now it is not necessary that every time we are going to get this caught the error, but this is the most efficient way of finding out the error. So in previous slide we have seen that how we can do branch testing with the help of true and false values. Now in this slide we will talk about domain testing. It is more sophisticated strategy for testing conditionals and is known as domain testing. As you can see in the figures, domain testing concentrates on linear inequalities. So we can see that we have linear equality here, we have linear equality here, and we have linear inequality here. So all these three linear inequalities. We test the inequality with three test points. So these are three odd test points in every scenario you can see. So 3 test is equal to 2 on boundary of the region and third outside. So as you can see, this is our correct test because 2 are inside and 1 is outside. So whenever the inequality changes, here the inequality has changed because of some mistake. So what is going to happen? All the points are going to come inside the boundary. So here as well. So these are our incorrect cases. This is our correct case. So we test the inequality with 3 test points, 2 on the boundary of the valid region and third outside the region, but between the values I. So these are the values of I on x-axis and the value of j are on the y-axis. When we make some mistake in typing inequalities, these 3 tests are sufficient to uncover them. So these 3 tests are sufficient to uncover them. So we can see that in correct test, this is incorrect test, this is also incorrect test because all these 3 points are now inside the boundary. So one of them must need to be outside boundary. But how this happened? Because we have incorrect inequality. So this is how we can do domain testing for linear inequalities. So in this slide we are going to talk about diffuse pairs. So these are 2 pairs. So a potential problem with path coverage is that the path chosen to cover CDFG may not have any important relationship between program function. Another testing strategy known as data flow testing makes use of definition use analysis. So def-use is basically a short form of definition use analysis. It selects paths that have some relationship to program function. So it selects path, as you can see here, that has some relationship to the functions. So what we do, the term def, as you can see here, the term def and use come from compiler which use def use analysis. So the compiler uses def use analysis for optimization. A variable value is defined. As you can see here, we have defined the value of the variable, that is a is equal to my pointer. When an assignment is made on the variable, so this is definition. When assignment is made on the variable, use when used on the right side too. So these def use appear in pairs. So for example, a is equal to my pointer is our definition and the use is here, some proc a comma b, or the use is here, a is equal to a pointer next. Okay, so each exercise, each definition use pair. So as in previous slide we have talked about def use. Definition is basically when we assign a variable a value, and use is when it is used in the code. So here you can see that in 1, 2, 3, 4, 5 and 6, value of x at 6 could be computed. We are computing the value of 6 could be computed at 1 or at 4. So if you see here, value of x at 6 could be computed at 1 or 4. So we are computing value of x at 1 and 4. Bad computation at 1 or 4 could be revealed only if they are used at 6. So if there is any wrong computation at 1 or 4, it can be computed only at 6. So that's why 1 and 6 and 4 and 6 are def use. So here at 1 and 6, here we have definition and use it at 6. At 4 we have again definition and we have 6. So these are our definitions and our use it at 6. So these are def use pair. Similarly, definition clear path. If you see here, 1, 2, 3, 5, 6. 1, 2. So I'm going to turn on my pointer. So 1, 2, 3, 5 and 6 is the definition clear path. Why this is a definition clear path? From 1 to 6, x is not reassigned. X is only assigned at 1, at then 2 it's not assigned, at 3 it's not assigned, at 5 it's not assigned, at 6 it's not assigned. So 1, 2, 4, 5, 6 is not definition clear path. Why? Because the value of x is killed, reassigned at node 4. So 1, 2, 4, 5, 6 is not a definition clear path. Rather 1, 2, 3, 5, 6 is a definition clear path. So 1, 6 is DU pair. Okay, because 1, 2, 3, 5, 6 is a definition clear path. So we can say that our DU pair is 1 and 6. The final method of program testing and validation is loop testing. We can write some specialized tests for loops. Loops are common and often perform important steps in program. It is worth developing loop-centric testing method. If number of iteration is fixed, then loop is relatively simple. However, many loops have bounds that are executed on the runtime. So, testing strategy includes skip loop entirely, one loop iteration, two loop iteration, number of iteration much below maximum iteration, n-1, n plus 1 iteration where n is max. So we can perform these testing strategies. So black box testing is the opposite of or complement of clear box testing. In clear box testing, we basically use the source code for testing purposes. Here the tests are generated without the knowledge of code being tested. So if we are not knowledgeable about the code we are testing, cannot test all possible inputs. So we are going to select few inputs.